Hello, Statistics and Precalculus, looking at the Fundamental Theorem of Algebra from section 7.2, the Fundamental Theorem. That means it's kind of important. Taking a quick look. Looking back, we're talking about a philosophical idea here, the idea of a mathematical set that is complete. You can write an equation with whole numbers that you can't solve with whole numbers, like this equation. It's written only with whole numbers, but the solution is not a whole number, like a half. So we had to invent rational numbers. The set of whole numbers is not complete. Likewise, you could write an equation with rational numbers that you can't solve with rational numbers, like x times x is 2. The answer to that is not a nice rational number. It's the square root of 2, which goes on forever as a decimal. We had to invent irrational numbers. But you can write an equation with irrational numbers that you can't solve with irrational numbers, like x times x is -1. Because when you're talking about irrational numbers, rational numbers, any real numbers at all, when you multiply them by themselves, you get a positive number. So guess what? Real numbers, irrational numbers are not complete. We had to invent new numbers, complex numbers like I, or 3 plus 5i, or things like that. And the news is, an equation written with complex numbers can be solved with complex numbers. The complex numbers are the first number set that is complete. For philosophy of math people, that's like really amazing, and it leads to the Fundamental Theorem of Algebra, proved 200 and some odd years ago by Carl Friedrich Gauss, great mathematician and physicist. If a p of x is any polynomial of degree n bigger than or equal to 1 with complex coefficients, so any equation written in complex numbers, then it has a complex answer. And that leads immediately to, if it's got degree n, then it's going to have exactly n answers when you count multiplicities. Multiplicities being like it can happen more than once. This is the statement from our book. It might be a little clearer depending on how you like it. Every polynomial of degree 1 has at least one zero that might be complex, and in fact it has exactly n zeros. If it's a 5th degree polynomial, it has 5 zeros. If it's a 12th degree polynomial, it has 12 zeros. If it's a 713th degree polynomial, it has 713 zeros. There it is. Good to